All right, so I made two great videos, and both of them had the wrong screen, so now I got to do them over again. So let's get back to where I was on. Oh yeah, so right. So in class on Tuesday the 14th, we started looking at this basic RC circuit. And the first thing we needed to do is to figure out what components we were going to use. Now, this stuff here on the right, the lower right, it's about when I was talking about to make a square wave, you need an infinite number of sine waves in a Fourier transform. Then the next thing we talked about was, okay, how do we decide on the components? And I had made some guesses which turned out weren't that far off. But I said, okay, why don't we make 100 microseconds of an RC constant? And that should be familiar because this business of the time constants. And one of our colleagues had already picked out a 5K resistor. So we said, okay, if we want a time constant of 100 microseconds, and we already have a 5K resistor, we know that tau, the time constant, equals RC, so we solve for C, and you see the 100 times 10 to the minus 6 divided by 5 times 10 to the third, and you end up with 20 nanofarads. So people are using 10 to 20 nanofarads. And then the other thing would be the other thing was use a square wave, and the square wave is going to get you the discharge and the charging. And so no switches needed. And then we have to figure out how to delineate the shape that we expect to see, because we're looking to see the shape, the voltage across the capacitor. And notice that V out is the voltage across the capacitor. So here what's happening is that the frequency is low, so that the time for this half of the square wave, is much longer than tau, and so you do your 5 time constants very quickly, and you can't really see very much. Here, the time of the width is much less than tau, so in fact, you never get to the plateau region. So in principle, on Tuesday, you worked on that, and the idea was that you want the time, so that would be half the period, right? Because this is 1/2 of the square wave. You want it to be about 5 time constants, so it plateaus, and then we figured out we could get the time. We needed to figure out where the 0 and the 63% was, and then we have a time here, and then we have a time at 63%, and that's our time constant. And these are stuff that I put on the board and not on a slide, so that's why I'm doing this. And the other thing was about how do we measure. We measured the time constant, so we have RC as a compound quantity. How do we then measure R and C alone? How do we unfold it? And what we do is we we create a new voltage divider, because remember that this is a voltage divider. This RC circuit is a voltage divider. So we make a new voltage divider with Z1 being our test, and Z2 is the RC components. And so you see there's V in, channel 1, V out, channel 2. And as in all voltage dividers, or two-component voltage dividers, the V out over V in is Z2 over Z1 plus Z2. So in order to measure R, we need to make the capacitor's resistance, its Z value, less than R over 10%. And we do that because, remember, our rule of thumb that in a series circuit, the resistance, the total resistance, is dominated by the larger one. So we want to take advantage of that. And we do that by making the capacitor, the Z of the capacitor, very low. And so then the capital R, the internal resistor dominates. And we do that by cranking up the frequency because we see then that the Z of the capacitor will go smaller and smaller with higher frequency. And then once we know that's to be true, then this equation becomes this equation. And we can go through this algebra and come up with this final equation. And just if we set R equal to RT, we notice that when we do, when we set V out over V in equal to a half, which is the equivalent of saying that R and RT are equal, then we see that, in fact, we retreat R equals RT just as we expected. And, got to pause. Okay, so we made our formula, and just for fun, we plugged in we said that V out over V in should be equal to half if we have a voltage divider with two equal resistors, and in fact, it returns the correct answer. All right, and then the other idea was what's the manifestation, what's the manifestation of all this on our screen? So at low frequencies, we'll see the input and output will be about the same, the peak to peak, but we'll see a phase shift. And then as we increase the frequency, V out will get smaller and smaller until it stops changing. So we get it to a certain frequency, and if we keep increasing it, we don't see any more change, and there's no more phase shift. So at that point, we can then measure the V peak to peak of V out and V in and find the ratio. And then we can plug that back into this equation to get the value for R. And of course, then the last step, which I didn't write here, would be that we would have RC equals to tau. We have R equals to, we know the value of R inside the RC circuit. And so then the C is going to equal to tau divided by RC, because that's going to equal to RC and over, there it is. So they'll cancel out. Pretty nifty, huh? Okay, so we'll stop this one and we'll start a new one.